Okay, so guys, the big picture today is this. What we're going to do is basically we're going to take our molecular models that we've been developing over the last couple days, thinking about what gases look like. And basically what we're going to do is we're going to take our mental picture and turn it into a mental video. And we're going to take these particles, and by talking about kinetics, which you know is the energy of motion, we're going to talk about how these things interact when they move. So we're going to start by making sure we're clear on what make gases ideal, and then we're going to talk about how our picture gets even better when we start thinking about how these things move. Then what we're going to do is we're going to take those new ideas and we're going to map them back to Boyles and Charles' law, so that you can see that we're not changing anything that we understand, we're just explaining it through a more complete lens. Then when we're done with that, we're going to make these gases move faster and slower. And how do we do that? How do we make gases move faster and slower? We change their temperature. Now guys, last year I lied to you and I told you that temperature was a measure of speed, and it's not. Temperature is not a measure of the speed of the molecules. They're related, but they are not the same. So we're going to talk about what temperature actually is a measure of, pull those ideas together, talk about effusion and diffusion, and then call it a day. You ready to go? Okay, so guys, this is where we are right now. I would encourage you to take notes judiciously. So guys, when we talk about kinetic molecular theory, we're obviously talking about the theory of moving molecules. Now, when we talk about theories always include assumptions. So guys, the first three of these are the assumptions that we have all signed off on. So you sort of dig into your brain and you pull up your mental model of a gas, and I think we would all agree that first of all, our gas consists of lots and lots of randomly moving, and probably in your model, very small particles. And as a part of that, guys, we understand that the volume of the gas molecules themselves is insignificant compared to the volume that the gas occupies. Remember, we say that gases have mass but no volume. And then we also say that these gases do not exhibit intermolecular forces. Now, guys, all of this lumped together has a name. What is it? Ideal gases. So guys, you could just write down gases are ideal, and if this is your understanding of ideal gases, you're money, because this is Avogadro's principle, and those other two are sort of the overriding assumptions that make gases ideal. So if you just write down gases are ideal, you're good to go, or you should be. But because you guys like to write down lots of stuff, you're writing down it all, and I will wait. Are you good? You okay? All right. So guys, from here now, we're going to take this potentially static model and we're going to set it into motion. So guys, if you take your mental model of a gas and you set it into motion, and we've already kind of talked about this when we talked about pressure. We're going to do this in greater detail in a minute. But guys, when you set your gas model into motion, what are these molecules doing? Well, they're traveling in straight lines, right? Until what happens? They hit something, and what are the two somethings they can hit? The wall, and what does that cause? Pressure, or each other. So guys, let's talk about the each other collision. This is going to be our baseline understanding that when molecules hit other molecules, they do not lose energy. For those of you that have taken physics, you may understand that the name that we give to that is an elastic collision, as opposed to an inelastic collision, and in an inelastic collision, energy is actually lost. Now guys, understand that doesn't mean that when two particles collide, they bounce off with the same speed. One can slow down and one can speed up, but the net energy change is zero. So they don't always have to exchange the same amount of energy, but if you know the energies before and after the collision, they always add up to the same. So the question is, so what? And the answer is this. That means the temperature doesn't change. So when these molecules collide, they don't slow down. If the molecules are not slowing down when they collide, then that means their kinetic energy doesn't change so long as we are not losing energy to the surroundings or gaining energy from the surroundings. So we're basically saying gases are closed systems. That we're not losing energy, energy is not coming or going, energy is staying put. And so these gases don't heat up or cool down just by running into each other. So, yeah. Off the wall. We're assuming no. So we're assuming that they also, and that's a good point, that not just the collisions with other molecules, but also with the container as well. So they bounce with, those are elastic collisions as well. Yeah.
So these are like all gases.
Yeah, and so this is all, well, so here, sort of, but no. So when gas molecules collide, that's actually not a real stretch to say that they're elastic collisions. The energy actually is pretty well conserved. The one that's not well conserved is what Carson was talking about. When they hit the container, they do tend to speed up and slow down. But we're going to pretend that they don't. So that would be the assumption that's actually not real, if you will. Okay, so guys, in addition to that then, we can now say this, that the kinetic energy of a gas is proportional to its absolute temperature. And what does absolute temperature mean? Kelvin temperature. So temperature is not the same as speed, but temperature is a direct reflection of kinetic energy. And we'll talk about that nuance in a minute, guys. But it basically goes like this. At any given temperature, the molecules of all gases have the same kinetic energy, but not necessarily the same speed. We'll answer the why not question in just a second. But guys, this is the answer to the lie that I told you last time. I said that temperature, last year I said temperature was a measure of speed. It's not. Temperature is a measure of kinetic energy. So here's what we can bank on. If you've got two samples of a gas, and if they have the same temperature, they will have the same kinetic energy. But that doesn't mean they have the same speed. I'll let you finish writing and then we'll talk about why. What do you mean by pure? Well, and that's actually an interesting point. This is always comparative. So, and we're going to talk about the other side of this in a minute, but let's do both. So guys, let's talk about the bigger picture here. You ready? So let's talk about pure oxygen. So guys, if you have a sample of pure oxygen, all of the molecules in that gas are not traveling the same speed. Some are traveling faster, some are traveling slower. We'll talk about the average in just a minute, because that's really what temperature is a measure of the average speed of the molecules. Okay, so let's say that again. This is new. This is foreshadowing into what we're going to do, but you ask, so let's say it. So guys, imagine we have a balloon of oxygen, okay? And all those molecules are moving around. They are not all traveling the same speed. Some are traveling faster than the average. Some are traveling slower than the average. When they collide, one may speed up, the other may slow down. But guys, they are not all traveling the same speed. Temperature is a measure of their average speed. Does that okay? But now imagine we're doing this. Imagine we have a balloon of oxygen and a balloon of hydrogen. Okay? And actually, you know what? Here, let's draw this over here. Yeah, all right, I'm going to try it. I'm going to make my board work. Here we go, you little bugger. All right, here we go. So guys, imagine that we have a balloon. If I push really hard, it works. If I've got a balloon of oxygen and I've got, let me switch colors. Not that it really matters, but we'll pretend. So guys, and then we've got another balloon over here, and this is a balloon of hydrogen, okay? So we've got a balloon of oxygen, a balloon of hydrogen, and let's assume, gosh, we're going to actually be almost done with the day once we're done with this conversation. So guys, let's assume that their temperatures are the same. If their temperatures are the same, what do we know to be the same of these two gases? Their kinetic energies. But why are their speeds not the same? Different masses. Because guys, remember, kinetic energy is 1/2 mv squared. And so oxygen is heavier than hydrogen, right? This is a mass of 2, this is a mass of 32 per molecule. So guys, oxygen has a higher mass. Therefore, what will the speed of the oxygen molecules have to be if they've got the same kinetic energy as these molecules that are lighter? Which one's moving faster, the oxygen or the hydrogen? The hydrogen. So guys, think about it this way. If you've got a dump truck and if you've got a baseball, the baseball's got to be traveling a whole lot faster than the dump truck to have the same energy, right? Because the baseball weighs next to nothing. The dump truck weighs as much as a dump truck. And if you get hit by a dump truck, and then get hit by a baseball, the baseball is going to have to be traveling a lot faster to do as much damage as the dump truck, right? Okay. Well, guys, the same thing is true here. If the temperature is the same, the kinetic energy is the same, but because the oxygen is heavier, it will be moving slower, and because the hydrogen is lighter, it will be moving faster at any given temperature. Go ahead.
So I'm curious about this pure gas thing. So the particles of oxygen molecules are not all moving the same speed?
Yes, exactly.
Because of gravity?
Not because of gravity, it's because of a law of averages. So let's talk about the individual gases now. So guys, now let's focus just on the oxygen. So if we could look inside this oxygen sample, we would find that some of these particles were moving fast and some of them were moving slow. And so in order to figure out, or faster or slower, it's comparative, right? So within a sample of gas, some are moving faster than others. And within this sample of gas, some would be moving faster than others. But if we could find the speed of every single one of these molecules and take the average, and if we could find the speed of every one of these molecules and take the average for the hydrogen would be faster than the average for the oxygen, because it has to be to give them the same kinetic energy because they're at the same temperature. Does that all make sense? Go, Carson, or someone was...
So is that why hydrogen was like such a low temperature? Because at the same temperature, like the oxygen is going to be moving off.
It's actually not. It has to do with the strength of the intermolecular forces. And you're going, wait a second, I thought we said these didn't have intermolecular forces because we just put that on the board, right? We're going to talk next time about real gases. You look at something like oxygen and you look at something like hydrogen and you go, hey, these molecules are pretty darn symmetrical, and therefore they shouldn't exhibit intermolecular forces. Turns out they do as a function of something called polarizability. And we're going to talk about that in a day. And what you'll find out is that because oxygen is bigger, it's actually more polarizable. Therefore, its intermolecular forces are greater and it has a higher boiling point. So it's an unrelated concept. So guys, do you get the idea about speed and mass and all that good stuff? So here's the beautiful part. I could actually right now say, guys, we're done. And you've learned all the stuff for today. That is really all that we need to talk about today. You need to understand that within a sample of gas, some molecules are moving faster, some are moving slower, and we talk about an average velocity. Then you need to understand that if we're comparing gases, that the average velocity of a lighter gas will be faster than the average velocity of a heavier gas at the same temperature, because again, temperature is a measure of kinetic energy, and there's a mass component to kinetic energy. So if the temperatures are the same, the kinetic energies are the same, that doesn't mean their velocities are the same, because there's the mass component that we have to account for. Because that's it. That's everything that we're doing today. Now we just need to talk about the details. You okay? All right. So, but I want to make sure that you understand that we've really done everything. So if you start to hear this again and you go, wait, maybe I didn't understand that, because now he's teaching it to us again. I'm really not, guys. We're just going to go over the details. So first thing that we've got to be able to do with that is this. We need to take our understandings of this idea of kinetic theory, and we need to bring this full circle and put it in the context of Boyles and Charles' law. So guys, let's make the connection back to pressure. So we've already talked about temperature, volume we understand. Let's bring in the idea of pressure. I'm guessing you don't need to write this down because you understood it from last time. So guys, what has to happen in order for a gas to produce a pressure? It's got to collide with the walls of the container, right? So what is it that determines the pressure the gas will exhibit as it relates to hitting the container? How hard it hits and how often it hits. And guys, remember from last year in general chemistry, we talked about the idea of the frequency and the magnitude of the collisions. We talked about that last year in reference to reaction rates, but it also holds true as it applies to pressures. So this may be something new that you might want to, it's up to you if you want to jot it down. It's probably obvious. But guys, the idea is this, that the pressure that a gas exhibits is related to the frequency and magnitude of the collisions. So guys, now let's pull this all together, because what is the frequency and the magnitude of the collisions dependent upon? How do we change the frequency or the magnitude of the collisions? Change the temperature. So now this all comes full circle, because temperature and pressure are now related, because pressure depends on the frequency and the magnitude of the collisions, and we change that by changing temperature. So now we can relate Boyles Law, which is pressure and volume, and Charles' Law, which is temperature and volume, because now we've got a relationship between temperature and pressure. So let's see if we can do this. So guys, just throwing out a couple questions. Goes like this. What effect does a volume increase have on pressure if we leave the temperature constant? But here's what you got to be able to do. Explain it given the kinetic theory of gases. And guys, this is, and you're learning this, right? That to be successful on the AP test, it's not about knowing the answers. It's about being able to explain the reasoning. So we understand, right, that if a gas gets bigger, that the pressure goes down. That's Boyles' law. The question is why? Take a shot at it, Josh. Good. Okay, so it's a matter of frequency, right? Is it a matter of magnitude? Why not? How do you know? Constant temperature, right. So we know that it's not a factor of magnitude, because they're not slowing down, but as the volume gets bigger, there's a less less likelihood that the molecules are going to collide at any given point in any given moment, and as a result, the pressure goes down. So guys, what we've always known to be true, Boyles Law, we can now explain conceptually because we understand the kinetic theory of gases. So what about this one? What effect does a temperature increase have on pressure, assuming the volume doesn't change? It increases. Why does it increase? Is it a magnitude or is it a frequency issue? It's both. The temperature is now going up. The volume is not changing. We're not allowing this gas to get any bigger. So as we heat it up, we know that we're getting harder collisions and more frequent collisions because the temperature is going up, and that then causes greater pressure. So guys, notice what we did here. Is this Boyles Law or is this Charles' Law? Neither one, or both, depending on how you think about it, because Charles' Law is temperature and volume, Boyles' Law is pressure and volume, but now we're holding volume constant, and we can now relate temperature and pressure, which Boyles or Charles' Law doesn't allow us to do, but we can make that connection now because we understand kinetics. Yeah? Mm-hmm. Yeah, actually, so I don't know if you've had this experience, but if you do this and then feel the can, it's cold, right? So why? Guys, if you have, and you've probably, I don't know if you've had this experience, I know I have. Guys, if you look in the summer, if you have a barbecue grill that's a propane grill, I don't know if you've seen this, but if you run your barbecue grill in the summer for a long time, you can actually see frost form. You know, it's humid in the summer, there's a lot of moisture in the air, and you can actually see frost form on the sides of your propane tank. For the same reason, and I know you can't, but so guys, what's going on here is you've actually just got, this is air, this is canned air. They literally just take air and they jam it inside this can, and I don't know if you can hear this, but can you hear it slosh around? It's a liquid. They have actually liquefied, and so maybe we can talk, we're going to do this in a day or two, but we can do it now. Guys, why is this air a liquid? So much pressure, molecules come close together, intermolecular forces start to work, and it sticks together as a gas. Now, when we do this, or as a liquid. Now, when we do this, it has the opportunity to expand. The intermolecular forces are breaking, and this gets cold. So guys, why? Okay, so what does it take in order to break intermolecular forces? Energy. What is our system? Not the can. What's our system? The gas that's inside the can, and as these intermolecular forces are breaking, that takes in energy. So this is an endothermic process. Where is the energy coming from? The surroundings, and more specifically, what part of the surroundings? The can, and therefore our hand, because we're putting our hand on the can, and heat is being drawn out of our hand and out of the can, going into the gas to break the intermolecular forces, and that's why it feels cold.
What about when it's already gas?
What's that?
What about when it's already gas? The IMFs are already broken.
Yeah, so yes. So what you're saying, Josh, is so this is really a big picture of what you're talking about, because now our container is no longer the can, it's the room. But imagine that we could take that can and allow it to expand. Okay, if we just went and we allowed it to expand, what you would actually find is that there's an equilibrium. And we haven't talked about this yet, but what we could say is this, is we could say that this substance as a liquid is in equilibrium with this substance as a gas, because the liquid is down here and the gas phase is up here. And so what you would find is that as you expand this container, it pushes the equilibrium in this direction, whether it's by letting it escape into the room or just putting it, making the container bigger, it's still going in this direction, and this still involves the breaking of intermolecular forces, and therefore it gets cold. Mm-hmm. I don't know that I've never had that experience. So I'm not arguing, but I don't know that that's necessarily true. Do you know that's necessarily true?
Well, I believe because the reason we brought this up is because we were doing a bottle rockets thing, and so
okay.
It's inside of these containers, and pressure after you
okay.
launch it. If you pick it up after it's launched, you'll find there's mist inside.
I don't know if I can.
Water, because the gas is cool. Because we use just air.
Well, but again, you're allowing that to, but it's a liquid. It's not a gas that's expanding into a bigger gas. You're actually getting a phase change. And again, that's the breaking of intermolecular forces, which requires energy. But taking a gas and making it into a bigger gas?
Well, you have a gas already in you just make the bigger.
But that's not what you're talking about.
Yeah.
Right.
But
okay.
That's what.
Yeah, so I would be hesitant to argue for or against that because I don't know that it happens. If you can verify that it happens, that making a gas bigger without going through a phase change does in fact cool it, we could probably come up with a way to explain it. But I'm always hesitant to explain something that I don't know is necessarily true, because then when we look like idiots when we find out in fact it wasn't really true and our whole theory's shot. So yeah. You guys good? All right, so guys, now let's go here. We've got this idea, and now again, we're not doing anything new, right? This is all just retelling of the same idea. So the question now is this, and you already know the answer. We're not being tricky. We had that conversation that brought us to these ideas. But guys, now I think you can finally formally answer this question. What is temperature actually a measure of if it's not velocity? Kinetic energy. Okay, so the idea then is this. Be careful what you write down. But we need to look at this graphically. So the idea is that while molecules in a gas do have an average kinetic energy, not all the molecules are going the same speed. So at any given time, some of the molecules are moving faster, some of the molecules are moving slower. So guys, what then is temperature a measure of? It's a measure of kinetic energy, which is reflected by average velocity. So guys, this is a funky graph. Let me allow you to just sort of think through this a little bit. This is interesting. I would be willing to bet you've never seen a graph like this before. Be very careful to read the labels on the axes, which I know you're doing. But the title is misleading. So let's talk about it. The title says temperature and molecular speed. So what would you expect the units to be on the axes? Temperature and molecular speed. You would expect this to be temperature. You would expect this to be molecular speed, right? But if that was the case, what would this graph look like? It'd go like this. That is not what this is saying to you, obviously, because that isn't what's represented. So let's talk about what this is representing, because there's some interesting things that we can learn. First of all, this. Where is temperature represented in this graph? The two different curves. They tried to bring that out by making the cold one blue and the hot one red. But guys, what we're doing is we're looking at two separate samples of gas. A hot sample of gas and a cold sample of gas. So why don't we do the cold sample first, pretend like the red one's not there, and look at the blue one. Now let's talk about the units. Guys, what are the units on the x-axis? Speed. So down here is not moving at all, and over here is flying around at about 1,000 meters per second. It's pretty quick. Now guys, this is the tricky bit. What about the y-axis? And guys, the y-axis is the fraction of molecules that are traveling within 10 meters per second of the indicated speed. So what does that mean? Well, say for example, what is this? This is 500, so 100, 200, 300, 400. So guys, this is 400 meters per second. And you'll notice, let's say that that's the peak. And you'll notice that they don't even give us units on the y-axis. But we do know that this is a maximum. So what does that mean? Well, it means that if we could find the speed of every single molecule in a sample, that most of them, that as they cluster together in groups, that we would find around 400 meters per second, that's where the greatest percentage of the speeds of the molecules lie. Let that soak in for a second. Get the idea? So let's now talk about what this graph is telling us. So guys, if we look at this curve, we find, and now let's compare it to the red curve. So we've got our blue curve, which is cold, and our red curve that is hot. So what do we already know to be true about hot gases compared to cold gases? Don't overthink this. You already know this. Hot gases, cold gases, what do we know about hot gases? They're moving faster. So guys, what in this graph represents the fact that hot is traveling faster than cold? The red graph's to the right, right? So guys, if this is the average speed, let me zoom out so I can write, praying that I can write. But guys, the idea is this. If this is the average speed, and if this is the average speed for those two curves, and they're not actually symmetrical, so it truly isn't. But guys, the idea is this. The fact that this red peak is to the right of the blue peak says that these guys are moving faster on average. Now, what does it mean that the blue peak is higher than the red peak? What do you now know about a blue gas? What a cold gas? More tightly gathered, if you understand standard deviations. Guys, the idea is this. Hot gases are traveling faster, but their distributions of speed is more spread out. Cold gases are moving slower, but there are more molecules moving at any given speed. This is the way I think about it. Don't tell anybody about this, but this is the way I think about it. Hot gases are moving faster, therefore they have more choices in terms of how fast they want to go. Don't ever tell Gil I said that. But it's kind of the way that I think about it. Hot gases are moving faster. Because they're moving faster, there are more potential speeds that they can go, so there are fewer of them traveling at any given speed. Cold gases, because they're moving slower, have fewer choices in terms of how fast they're going to move, and therefore their groupings are tighter because they have fewer choices in terms of how fast they're going to go. It's like a density curve. Yeah, it really kind of is like a density curve. Well, guys, here's the thing that you need to understand. It's simply this. Hot gases are traveling faster than cold gases, but the deal is this. Remember that temperature, guys, remember that temperature is actually a reflection of kinetic energy, right? And so the connection is this. In order to convert average temperatures into kinetic energies. So if you wanted to figure out the average kinetic energy for a sample of gas, this would not be the speed that you would use, and this would not be the speed that you would use. Why not? It's not actually the average. Can you see that this is actually skewed to the right? That there's more data on the right than there is on the left? For those of you that have done statistics, you can actually account for this by taking what is called a root mean squared average. We don't need to worry about it. I have to mention it because you'll get it in college and you don't get to come back and say, hey, you taught us this wrong. But guys, the bottom line is this, and this is a good time to grab your AP sheets because some of your heads are spinning. You ready? Here's the bottom line. You will never be asked in AP chemistry to figure out the average kinetic energy of a gas sample, okay? Look at the gas, where's it at? Gases, liquids, and solutions. See the kinetic energy equation there? Yeah, it's per molecule. And because it's per molecule, we don't have to talk about average velocities because they will give you the velocity of that particular molecule. So you don't have to worry about any of the distinction between the root mean squared average and the actual. All you need to understand is how to find the velocity of an individual molecule given its kinetic energy, and you don't have to worry about the averages. Groovy? Okay. If you're interested to learn how, it actually talks about it in the book, but you don't need to worry. Yeah.
So that graph's going to change for every.
Absolutely. Yep. Absolutely. Yep. Yeah, because understand here, Carson, that this is actually the same gas at two different temperatures. Yeah. Okay. Mm-hmm. Absolutely. Yeah. Yep. Yeah. No, please. You're saying it very well. I'm. You good? All right. So guys, one last thought and we are done. So now let's talk about dissimilar gases. We've already done this, right? What did you learn? If the temperatures are the same, the lighter gases are moving faster and the heavier gases are moving slower. It's the dump truck in the baseball, right? So guys, if you want it, in word form, it goes like this. Well, here, that was probably a lot of clutter. So if you have two dissimilar gases, like for example, we talked about oxygen and hydrogen. If you have two dissimilar gases and they have the same temperature, then we know this. Their average kinetic energies are equal. However, their speeds are not equal. And again, you know the answer to why this is true. Kinetic energy contains a mass factor. So imagine that we had a sample of helium and we had a sample of neon. Helium is lighter than neon, so helium will be moving on average faster than the neon. And it's all because of the kinetic energy equation, right? Okay, so the question then becomes, so what? And guys, this all comes down to the application that you need to understand. You no longer have to know this mathematically, but I'll show you the math anyway. You do need to know these terms. Guys, effusion and diffusion. Effusion is the process of a gas escaping from a container through a small hole. Diffusion is the spreading out and mixing of gases. Yes, that would, yes. So you've got the cap on the pot, and yes, that would be effusion. Yeah, the reason that I was hesitant is because you're still pouring energy into that. But even that's okay. Yeah, yes. Now guys, the trick is this. Both of these processes depend on the molecular speeds of the molecules. So let me show you, when you're caught up with me, I'll show you what I'm talking about. Are you caught up with me? Oh, wait. How about now? Not yet. So guys, the idea is this. If we go back to this picture, let's remind ourselves, let me switch colors here really quick. Which one's moving faster, the helium or the neon? Helium, right? Now, imagine that this is not, these aren't balloons, but they're rigid containers, okay? They don't collapse. And then imagine that we drill a hole in the side of this container, and imagine that we drill a hole in the side of this container, and the holes are the same size, and these are again not balloons, so they don't collapse. Why will the gas escape? Yeah, they're moving around, right? And as they move around, they're running into the walls. But if they run into this little bit of wall that is no longer there, instead of bouncing back, it escapes, right? Now, guys, do we have to do work to get this to happen? No, we talked about that with entropy, right? They're just going to spread out. Here's the question. Which one is going to leak faster, the helium or the neon? The helium, because the helium particles are moving faster. Now, guys, here's the thing that's interesting. If we could measure the speed at which both of these leak, we could figure out the masses of the gases. So for example, if we know the mass of neon and say that we didn't know that this was helium, we just knew it was a gas. If we know the mass of neon, and if we know the relative rates at which these things leak, we can then figure out the mass of the other gas. How do we do that? Well, guys, it used to be that this was on the AP equation sheet. I'm just going to lay it on you. This is actually the equation. It looks like this. This is what is called Graham's Law of Effusion. And it says that the effusion rate of a gas is inversely proportional to the square root of its molar mass. Yeah, it's supposed to be in the middle. It just got moved here. I can actually probably move it again. Yeah, so R's are the rates. I don't want to pick that apart. It just got smushed. But they're, well, maybe I should, because you may not be able to see that that means they're equal. One more. Let's see if I can get it now. No. Good heavens. Sometimes you just have to hit delete to figure out what you've actually got selected. Now it won't even let me ungroup it. Whoa. Oh, because that's all just words. Ha. You get the idea, right? How about that? The things I do for you guys. This is like unraveling a sweater. All right, I give up. All right, you get the idea. There you go. Hey, that's not, it's not bad. Yeah, but I know. You're right. Now, guys, here's the trick. No longer do you need to understand this mathematically. It's not on the equation sheet, right? Gone. You do need to understand it conceptually, though. So, guys, allow me to take you here. So it goes like this. So we've got here two gases. Now, guys, the thing that I don't like about this little demonstration is that they're saying that heavier gases are so much significantly bigger than lighter gases. Remember, their volumes are really insignificant, independent of mass. But the trick is if we set these in motion, if we set these things in motion, assuming that these are in fact more massive, how will they be traveling? Slower. Therefore, they will not effuse as quickly. So every time they run into what otherwise could be that opening, they travel through, and you find that in fact the ones that are lighter do effuse more quickly simply because they're moving faster. You good? I think Carson, go ahead.
So what are the units for the rate? Would it just be like volume?
It actually isn't. The rate units, and again, you don't have to know this mathematically, right? But the rate units are actually just proportions. So it would be twice as fast. And that's the thing that made these hard to solve, is because you'd have to say, I'm going to call one of these gases gas 1. And then once you've called one gas 1 and one gas 2, you would say that gas 2, say that it diffuses at a rate 4 times that of gas 1. So this would be a 4 and this would be a 1. So it's a relative rate of effusion. Right, so you would, so in that case, well, it depends on how you're doing the experiment. You could do it by pressure change. You could do it empirically by moles. But the data that we'd been given on these were just relative. It effuses twice as fast. So this would be 1 and that would be 2. Yeah. All right, so guys, that's it. We done. So here's the scoop. This is your homework and chapter 11. If you've already done chapter 11, I'd love to take it from you if you want it out of your hair. It's not due till Tuesday. We've got about 20 or 25 minutes to work on these. This is a little bigger assignment today. Fiddle with them. Frankly, guys, there may be a Graham's Law of Effusion problem in there for you to play with. Again, you won't see it on the AP test, but can't hurt. And we'll take a look at pride reports as things sort of come to a close. I'm going to shut this off.